Hello, everyone. My name is Bogdan and I'm a tech lead at Databricks. In this talk, I'm going to present Cloud Fetch, a new architecture that we have designed to achieve high bandwidth connectivity with business intelligence tools. Business intelligence is one of the most interesting and challenging use cases that we have seen at Databricks in recent years. BI tools like Tableau, Power BI, and Looker allow data analysts to create dashboards and to visualize results while hiding the complexity of generating queries and executing them on the Databricks platform. So these tools communicate with an RPC server that handles requests for query execution and for retrieving the query results. It's clearly that short-running queries are latency sensitive, so we need to make sure that we are inlining the results as fast as possible back to the client. At the same time, queries that generate large amounts of data, they have high throughput requirements. So we need to make sure that we are bringing back the query results back. We are bringing back the query results to the client machine in a timely manner. 2 years ago, we looked at the amount of data that was flowing through Databricks servers because of the BI use cases, and we projected an exponential increase that was lying ahead of us. While looking at this chart, we realized that the current architecture that we were having at the time was unsuitable to deliver the requirements in terms of latency and high throughput that these BI tools were demanding. So we scrutinized our BI stack and we identified two main problems that we were having. First, we were doing many result conversions that were relatively expensive at all layers in the stack. And secondly, we were looking at all the proxy layers that are lying between the Databricks cluster and the client, and we realized that they are unable to deliver good connectivity and high throughput bandwidth when BI tools are extracting a large amounts of data. So we came up with two solutions, and I'm going to present them in turn in the following slides of this talk. First, let me introduce how we have incorporated Arrow serialization in the collect path for query results. BI tools, as I said, they communicate with a Databricks RPC server. So, and they execute queries using the following pattern. They submit a query text verbatim that is wrapped by the Databricks RPC server into a data frame. So it can be executed on the cluster. While the cluster crunches the results, the client is sending status polls to make sure that the query is still running and to detect the moment of time when the query is finished. From the moment that it is finished, the client can start requesting the results back to the client machine. It does so by sending subsequent a number of fetch requests. So because we don't return all the results in one go, so we are paginating them, and this typically translates into a sequence of fetch requests. All this extract, so like the extract architecture as we were having it 2 years ago, was single-threaded. So everything was pipelined through this RPC server, and then it was streamed back through the proxy layers back to the client. A second usage pattern that we have observed in BI tools was importing complete tables, so like complete data sets that were importing and that were extracted on the client machine. And this usage pattern became more popular with Tableau acquiring Hyper, which was a highly efficient SQL engine. So they were able to generate queries and compute them locally without going back and forth between the client machine and the Databricks cluster. This import mode, it's slightly different than the query execution mode, but there's certainly some overlap, as you will see shortly. So all these BI tools first emit a metadata request in order to understand the schema of the table. And once the schema, so like the columns and their types are retrieved from the Databricks server, these BI tools, they wrap like a select star query with all the columns of the schema in order to extract the content of the table. So that query is running on the Databricks cluster, and once it completes, so like all the results are loaded in the cluster, then the clients, which in this case are the BI tools, they start sending fetch requests in order to get the results on the local machine. So to put a bit into perspective the architecture that we had before Arrow, let me explain how the result was transformed, starting from the Spark executors up to the client application. Spark executors were running tasks, and these tasks are generating Spark rows. So there is an internal representation of these rows in the memory of executors that was serialized with the Java serializer and then compressed with LZ4. Once they were collected on the driver, we were decompressing them and then deserializing them in order to convert them to a Hive format that was understood by these BI tools. So like we were returning them in Hive format, and from that point, we were sending them back via the protocol to the client machine, who would finally serve them, or like retrieve them and serve them to the upstream application. So as you see, there are like multiple layers of conversions on executors, and it seems like on the driver we are doing some unnecessary translations and then sending them back over to the client in this legacy Hive format. So all these layers, they were adding like small latencies across the way, and we definitely wanted to have a more uniform serialization format that was portable, that was independent of the process or of the system that was serializing or deserializing them. And we found that Arrow is actually very suitable for our use case. So what we did on Spark executors, while tasks were generating rows, we would serialize them with Arrow, and then we would compress them still, collect them on the driver, but in this case, the driver would do nothing. So it would just return them to the client, would push all the latency of like deserializing and decompressing and then serving the actual rows to the upstream application to the client. So in this case, we kind of removed the bottleneck of doing those conversions from the driver, and we shifted the overhead to the client machine. So how does this actually work? In Spark, once you submit a SQL text, so once the RPC server receives a SQL text, it wraps it in a data frame. The data frame is analyzed, it's optimized. We generate the SQL optimizer generates the optimized plan and the execution plan, which is an RDD that is a collection of partitions that need to be computed by individual tasks on executors. And these tasks, when they are computing a partition, they go over the input. They go over the input rows and they generate result rows. These result rows. So at the end of the task computation, we are plugging in an adapter that allows us to convert these rows into arrow batches, so that like multiple arrows, they are packed into an arrow batch. Once that operation is complete, then the result is returned back to the coordinator node, which is the Spark driver node in this case. We enforce some limits to these batches, so we don't allow them to have arbitrary sizes or like unbounded sizes. And in our case, we have limited them to 1,000 rows and 128 kilobytes. So we want to prevent cases where a small number of rows, but like with very wide schemas, would like basically occupy the entire sizing bytes that is allocated for the batch. So we are capturing both dimensions, so like also rows, many rows with just a few columns, but also like few rows with very wide columns. And as I mentioned before, we do the Databricks RPC server implements pagination. So when requests come in, we are limiting the amount of data that we return with a payload of a response. And in this case, we are limiting to 10,000 rows and 10,000 and 10 megabytes for fetch response. So let's look a bit at the order of improvements that we have seen with once we migrated to Arrow. For various extracts, we have seen that for a broad range of extracts, actually. So like we've seen like improvements up to 3x. So like speed ups up to 3x, which indeed it's like a decent, it's a decent improvement. But if you think about it and like looking at the chart of with the data growth that was ahead of us, it didn't feel like it was sufficient. So we had to continue to improve our extract architecture. And one of the ideas that we had was to bypass completely the overhead, the bottleneck that the intermediate layers would introduce in the BI stack. And we achieved this by using cloud storage. So let me picture clearly the extract infrastructure that we had before Cloud Fetch. As you may be familiar, like the Databricks runtime system consists of a driver and executor nodes, and the driver is responsible with splitting the query into multiple tasks that are scheduled and distributed independently on these executors. And the driver also handles like fault tolerance mechanisms. So in case like some of these tasks, they fail, they are recomputed, they are rescheduled. And the executors generate the results. They compute the partition, they generate the results which are collected on the driver. If they exceed the memory of the driver, they are spilled to disk. So they are spilled on the local disk of the driver. And once the client starts fetching requests, they flow, like they are streamed over all the intermediate proxy layers that we have in between the RPC server and the client. Now, in the new data extract architecture that we are proposing, we are introducing the cloud storage as an intermediate layer for storing the results, for persisting the results. And the key insight into Cloud Fetch is that we allow both the writing and the reading of the results to be performed in parallel. So now executors can upload the results independently to cloud storage. And instead of collecting all those results on a single node on the driver, the executors return instead file paths to the uploaded results in cloud storage. Now the driver, when it receives a request for fetching data, for fetching query results for clients, it would return basically just URLs, so like links to the file, to the location of the result files, and the client would download them directly from cloud storage. So like there's an indirection from like the Databricks servers to the cloud storage. Of course, optimizing the latency of small results, it's super important. So we wanted to make sure that small result sets do not suffer from latency of uploading and downloading to and from Cloud Store. So in this case, we introduced a threshold beyond which results would be spilled to Cloud Store. Conversely, if the result set is smaller than 5 megabytes, we would collect we would return it in the Arrow batch format to the driver. So executors, they each enforce like this 5 megabytes threshold independently, and it's clearly that some of them they would return as cloud links, while others would return Arrow batches. So like the driver would collect what we call a hybrid result. We recognize that it's a significant complexity to let the client to deal with these hybrid results. So instead, we decided to return a homogeneous format. And because driver is in the middle, we let him handle the resolution of the format that was returned to the client. So we distinguish a number of cases here. If all results return as cloud links, then that's simple, that with the result format that we expose to the client, it's cloud. If it's a mix of cloud and Arrow batches, the driver would upload the remaining Arrow batches and return the cloud format to the client. And now the more complex case is when the driver collects Arrow batches. And those Arrow batches, also like the overall size of the result exceeds 5 megabytes. In that case, it would upload the results, the entire result set to cloud storage and return cloud as the format. But if the overall size of the result is below 5 megabytes, the driver would just return inline Arrow batches. So that's the only case when the driver, in case of a hybrid result, would fall back to the Arrow batches, to the inline Arrow batches. So to recap, like we have a data layout that translates Spark rows to Arrow batches and then to cloud files. And we limit, as we limit the size of an Arrow batch, we also limit the size of a cloud file to 20 megabytes. Now, the client, when sends fetch requests to the Databricks RPC server, it would receive URLs that correspond to the amount of data that it's returned in one response. And by default, the server limits that amount of data to 1 gigabyte. So we always return on a fetch response 1 gigabyte worth of URLs to the client. Now let's zoom in a bit into how the client can actually fetch the results from these URLs. Now, when it receives a set of links, the client would spin off a thread pool with multiple threads that would download in parallel from these URL links. In case one of the downloads is failing because the cloud store is rejecting the request, or it's like rate limiting the client can go back to the RPC server and request refresh URLs for the failed downloads. So it would come back and it would retry those requests a number of times with exponential backoff. But it's very important to acknowledge that the client would not go further and like fetch the next portion of the result set until it completes the current batch of links. Once that is, all the results are downloaded, they are decompressed, they are deserialized, like they are served basically to the upstream application in the raw format that it's exposed to BI tools. To look into performance of Cloud Fetch, we achieve significant improvements. An order of magnitude faster than the old architecture with Arrow serialization incorporated. So like looking at a native ODBC C++ application fetching 3.5 gigabytes, we've seen Cloud Fetch delivering a throughput of close to 500 megabytes per second. It's when we tested it end to end from like the BI tool with the BI tool integration, we've seen that the throughput, although it was still significant, was maybe cut in half from the native performance that we have observed. And this basically shows us that we are now bringing the data much faster than the BI tools can inject. So we have shifted like the bottleneck from the Databricks infrastructure, from the Databricks BI stack up to the BI tools. So we are now actively working with partners to like improve and like speed even further and be as close as possible to the native performance that Cloud Fetch can deliver. Interestingly, we have also looked at a number of extracts. Also, one of our largest extracts that we are seeing daily in our ecosystem, and we also see that Cloud Fetch extracts are an order of magnitude faster than the Arrow serialized format and also than the legacy format. To sum up, in this talk, I introduced Cloud Fetch, which is a new design of the data extract architecture that we have at Databricks that allows BI tools to fetch query results via cloud stores. So instead of streaming all the results via the multi-proxy, like the multiple layers of proxies that lie in between the client and the Databricks cluster, now we would upload the results in parallel from executors to cloud storage and return download URLs that are used by the client machine to download to retrieve the results directly from cloud object stores. And we have seen like impressive performance, so like 10x improvements in native C++ or DBC application, which is really impressive. Yeah, and this concludes my talk. Thank you for your attention, and I'm looking forward to any questions you may have. You can reach out to me directly on my email.